This conference will now be recorded. This conference will now be recorded.
So very good evening, students. Yesterday we had excuse me. Yesterday we had discussed somewhat about the valuable and very important experiments. Those are conducted by Faraday and Henry. And discovered the phenomenon of electromagnetic induction. And from the observations, like putting all the observations together, Faraday was able to give an equation or a mathematical formulation about the law of induction. So that means he had given some law out of the observations of the experimental phenomenon, okay, out of the experimental facts. So we had discussed already the experimental facts, but just to recap and to have the motivation for today's class, like Faraday's law of induction, I will discuss in detail. Lenz's law I'll discuss in detail today, and I'll discuss about motional EMF in detail. So before I go for today's topic, like Lenz's law and motional EMF, etc., this Fleming's law, 11th rule, I'll not discuss here. I'll discuss this later. So just let us have a little bit of recapitulation about this, about yesterday's class. Okay. See, Faraday's first experiment was that he had taken a coil of conducting wires and he had connected the two ends of the coil with a galvanometer, and he had taken a bar magnet, as you see here, and the bar magnet is moved towards and away from the coil C1. And what was the observation? Observation was current flow in C1. Okay, current coil C1. So that was the observation. Okay, so this was an observation. Now, one more thing is that when the bar magnet is moved towards and away, there was the change in the direction in this in the current through the coil. So that was another observation, and the current magnitude of the current also changes when it is bringing towards and away from the coil. So these were observations. Main thing is that there is a flow of current in the coil C1 as the bar magnet is moving towards the coil or away from the coil. So that was first experiment. So first experiment says that there is an induced EMF due to the relative motion between the coil and bar magnet. This is the conclusion from this experiment. What was the conclusion? That induced EMF is induced in the coil C1 due to the relative motion between coil and bar magnet. Okay, so not only the coil sorry, not only the magnet while magnet is moving, but if you fix the magnet somehow and if you move the coil away and towards the magnet, then also there is a flow of current in the coil C1. So that is why the word relative motion between the coil and bar magnet. Okay, either of them, if you hold fixed and other one is moving towards or away, you will get the same effect. But if both are held fixed, then there is no current flow in the coil. Now, second experiment is that, you know, a, a current carrying conducting lobe can act as a bar magnet, that we had already discussed. Okay, so one side will be north pole, other side will be south pole. That is what we have seen. So magnetic field lines will be like this. So this way it will go like this. Okay, all right. So this is the thing. So the bar magnet was replaced by coil C2, and here what is done is that the coil C2 is sent current. Okay, current is sent through C2, applying this battery arrangement. Okay, so it is seen that when the coil, which is C2 coil, which is carrying some current, anyway, you know, when a current carrying loop, okay, current carrying loop always produces magnetic field around it. Okay, so now C2, if C2 is actually moved towards and away, then there is a current flow in the coil C1. If C2 is held fixed and C1 is moved away and towards the C2 coil, then also same thing is seen. Same thing in the sense there is a flow of current, but there is a change in the direction of the current. So that is what was second observation. So second observation gives some conclusion about this induced EMF. It is said that induced EMF is produced by the relative motion between two coils. Now, the third experiment is confirming that it is not the relative motion between the coils. It is the change in the flux which is linked to the coil is responsible for the EMF induced in the coil C1. So what was done there? I don't know whether I have the figure. Okay, so here itself, if I just take this coil C, this C2 coil, and here if there is a tapping key or switch here, if I take a tapping key and the key is suddenly closed, then what happens? Suddenly closed means current will be suddenly increasing. Suppose I have current, if the fixed current 5 ampere, then also as soon as you switch on, the current has to rise within a fraction of second from 0 ampere to 5 ampere, right? From 0 ampere to 5 ampere. So this is change in the current, right? So this change in the current will actually induce, like change in the current actually makes changes in the flux link with the coil C1. All right. So if the key is closed continuously, then there is no flow of current in the C1 coil. But when it is taking off, like if the switch is off or key is taking off, then there is a flow of current again, but that is in the opposite direction. So this, there is no relative motion now. Both C1 and C2 are held fixed. Only what is done is that there is a key now. So this key is suddenly switched on and switched off. So then, due to that, there will be a flow of current in the coil C1. Okay. So see, out of these three experiments, what is important like what is the conclusion is that it is, so overall conclusion of the experiment. What was the overall conclusion? See, from third experiment itself we can understand it is not the relative motion. It is something to do with the linked flux. Okay, see, in each cases, already in the figure you can see in each cases. So when, see, bar magnet actually produces magnetic field around it, right, near to it, and see field lines, how field lines are going. Field lines are going like this. Okay, so you know, we have seen what is the flux. Phi is the number of magnetic field lines passing through a cross section, right, perpendicular to the plane of that cross section. Okay, so in this case also, when a bar magnet is just pushed towards the coil C1, the flux linked with the coil actually changes. Suppose at very far there was 5 field lines crossing. When you bring towards the C1 coil, 5 to 7, 7 to 10, maybe 20, or maybe 100 lines will be passing through this C1 coil. So flux will be changing, right? It is actually directly proportional to the number of field lines. Okay, number of field lines passing. Okay, number of field lines, magnetic field lines. So flux is actually, flux linked with any area or any loop or any coil is directly proportional to the number of field lines passing through that, right? So that is the thing. So what is the prime cause or actual cause for this induction is the change in the flux linked with the conducting loop or conducting wire or coil. So how flux changes and why there are different observations, like say if the bar magnet is moved towards, then flux changes, right? So that how it changes, it is actually increasing. Flux linked with the coil C1 is increasing. Suppose at this particular distance it is phi 1, and when it is here it is phi 2. So what will be change in the flux? D phi will be phi 2 minus phi 1. Okay, this is the change in the flux. Obviously, if it is taken away, the number of field lines passing through this C1 coil will be decreasing. In that case, the flux will be less. So in that case, I can write change in the flux will be phi 1 minus phi 2. Right? This is the thing. That means we can actually get a net or magnitude of change, magnitude of the change of the magnetic flux. Okay. Now look, in this case, second case, you know, this C2 also acts as a bar magnet in the sense it creates magnetic field around it. Now when the coil is moved, see, if either of this coil is moved away, then number of field lines passing through the C1 will be less. When it is brought, like one among this is moving, so whatever it is, so whether C1 is moving or C2 is moving, when they are brought close towards each other, then the flux linked with C1 will be increasing, okay, compared to the previous situation. So there will be a net change in the flux. So that is actually the cause. See, when in the third experiment, when the coils were held fixed, but there was a key. So as I explained before, when as soon as you switch on the key, within a fraction of a second, the current, fixed current in the C2 coil has to reach, suppose it is fixed current is 5 ampere or 15 ampere, whatever. So that has to rise from 0 to 5 ampere. So there is a change in the current. So that change in the current actually will cause the change in the flux. Okay. So it is the flux change which is actually responsible for the induced EMF. Okay. Now, that is the origin of the current in the coil C1. Now, putting all these observations all together, Faraday gave a law. Okay, gave a law about this induced EMF. Like Faraday's law gives the magnitude of the induced EMF, that is that is getting induced in the coil. Okay, so Faraday's law gives the magnitude of the induced EMF. So this is E in a conducting loop is equal to the rate of change of the magnetic flux. Magnetic flux is phi, right? So mathematically it can be written as, if I write the magnitude, then it is d phi by dt magnitude. Okay, so the magnitude of the induced EMF in a conducting loop is equal to the time rate of change of magnetic flux. Actually, Faraday's law of induction is written as this: E is equal to minus d phi dt. This is the complete law, or this is actually known as Faraday's law of induction. Faraday's law of induction, EM induction, electromagnetic induction. Okay, look here. This is the change in the flux d phi, and this is the time taken for this change. So if sometime there is a change in the flux, suppose see flux we know VA cos theta, right? VA cos theta. Okay, before that, let me tell you this. So this was not given by Faraday, Michael Faraday. It was given by actually Lenz, French physicist Lenz. Okay, I think HF Lenz. Anyway, Lenz. It was given by Lenz. This actually indicates the direction of the induced EMF or induced current. Indicates the direction. Indicates the direction of induced. So minus sign. We should say minus sign indicates the induced EMF. Okay, let me just write it neat and clean. So mathematically induced EMF according to Faraday, Michael Faraday, this d phi by dt. So this minus sign was given by Lenz. Minus sign indicates the direction of induced EMF. Okay, induced EMF. Now see, how do you change, like what are the possible OS to change the flask linked with some coil? See, phi is BA cos theta. We have already learned this. That means B is the magnitude of the magnetic field in a region or magnetic field where the conducting loop is placed. A is the area of the conducting loop through which the flux line passes, and theta is the angle between the magnetic field and the surface normal. Okay, this is the theta angle between. So this is the n cap and this is magnetic field. Okay, so this theta, if we change the theta, then the flux also changes. Like see, if theta is 90 degrees, then flux is 0. If theta is 0 degree, flux is maximum. Okay, so we can actually change. See, if this is fixed, so phi may be changed by changing A, area of cross section of the loop, or the angle theta. Okay, so these are possible ways. And also actually see, you can change the b also. If b is not fixed, then you can actually change the b also. If b is not fixed, b is time dependent, then also flux changes dependent. Okay, so then also flux can be changed. Okay, so these are few points where I just wanted to mention that flux can be changed. Okay, how flux can be changed. Now what I am going to discuss is that the Lenz's law. So Lenz's law is actually very important in EM induction or electromagnetic induction, because it gives the direction of the induced EMF directly. Okay, or induced current. It gives the direction of induced EMF or induced current. See what is the significance of this law, Lenz's law. First of all, let us learn what is Lenz's law. So Lenz's law states that the polarity or the direction of the induced EMF will be such that it tends to produce a current in a direction, like current which opposes the cause which produces it, that is the change in the flux. I'll just explain. See, Lenz's law states that the polarity or the direction of the induced EMF will be such that the induced EMF will produce a current which will oppose the change in the flux itself. Okay, magnetic flux. All right, so here you can see this is minus d phi dt. Okay, so as this increases, as much as this increases, so EMF in the opposite side will also increase. Okay, I'll just show you here some demonstrations here. Not demonstrations, in the sense, see, suppose I have a coil. Okay, so I have another like I have a bar magnet also. So ends of the coil is connected to the galvanometer, as you see here. See, when this bar magnet is brought towards the coil, see, it's kind of a solenoid. You know what happens? There will be induced EMF, and that will produce a current in the coil or in this solenoid. That will produce a current in such a way that the north pole is induced near to the, like in the near face of the coil, such that it opposes or repel. See, this north pole, they both repel each other. When the bar magnet is taken away, then the direction of the current in this coil will be, see, in the second case, will be in such a way that the south pole is produced at this end, such that the motion of, this motion of the bar magnet is actually, opposed, such that this S pole attracts the north pole and decreases the motion away from the coil. So this is actually Lenz's law says. So Lenz's law says that the direction of the induced EMF will be such that that will produce a current which will produce a magnetic field which will be opposing the real one or original one. In other words, the direction of the current will be such that that in the coil itself there will be a bar magnet. Okay, coil itself will act as a bar magnet such that this end of the bar magnet becomes north pole, so that it will oppose the bar magnet to move towards the coil, and hence it is actually changing the or reducing the change in the flux. Actually, change in the flux will actually see the original cause is change in the flux. So if the bar magnet is brought near to the coil, then the flux will increase. Okay, flux will increase, and hence induced EMF also will increase. That means what? When the flux length is increasing, then north pole will be produced here such that the flux doesn't increase. Flux change doesn't increase. Flux change doesn't increase, so that the motion of this bar magnet will become little bit slower. In the second case also, since it is going away, the number of flux line also decreases. Since it is going away, number of flux line or the amount of flux linked with each coil will be decreasing. Okay, each loop will be decreasing. So that's why the induced EMF in this case will be such that it will produce a south pole at this end, such that it attracts the north pole of the bar magnet and reduces the motion of motion while going away. And by doing that, actually the change, see, as it go faster, the flux linked with each coil will decrease faster. So that is actually making faster change in the flux, but that change in the flux will be opposed by the induced EMF or induced current or induced magnetic field. Okay, so this will be very, very clear again here. You look here, see this here. So if somehow flux linked in this, this is the coil. Suppose this has a plane, this is in plane. Okay, the area of this loop is in plane, and this original magnetic field is in the direction perpendicular to the loop of area of the loop, and also it is into the plane of the paper. Now somehow if the flux change in this, flux linked to this coil is this loop, current carrying loop is changed, then the induced current will be flowing in the anti-clockwise direction such that that induced current will produce a magnetic field exactly in the opposite direction of the original field, as you see. So increase in external magnetic field B induces current, and that induced current is actually inducing an induced magnetic field which opposes the original field. You can see that. Okay, this is actually Lenz's law. Here also, see, if the magnetic field is decreased, then the flux length in this will also decrease, but this decrease in the flux has to be ceased. That's why the current will be in such a direction that means it will be in the clockwise direction, such that the induced induced current will be induced magnetic field will be in the same direction as the original field B. So this is the thing. All right, so induced EMF in this case, when the flux linked to the coil is decreasing, then induced magnetic field and the original magnetic field, they combine to to have a greater change in the flask. All right, now we'll see that Lenz's law is not just an ad hoc law. It is actually has its base in the law of conservation of energy. Lenz's law is actually based on the law of conservation of energy. That means it can actually hold oil to explain, or it is actually on the basis of law of conservation of energy. Law of conservation of energy, how it is actually supporting, or how it is based on law of conservation of energy. I'll just explain here. I need this figure here. Okay. So suppose, so in this case, what is happening as you bring this bar magnet towards the coil is actually opposing the motion of this bar magnet. Okay, that means, you know, according to Lenz's law, the motion of the bar magnet is always opposed. That means there will see repulsive force will be there. So if you want to bring steel near the coil, then what happens? Uh, since it is, see, since the induced EMF is opposing the motion of the bar magnet itself, then still we want to bring the bar magnet towards the coil. So in that case, you know, you have to externally put some effort or put some work done. You have to do certain work done against the opposing force or repelling force of this north pole produced in the coil. Okay. So, you know, here you can see that we have to do certain work done to overcome the repulsive force, right? North pole, this is also north pole. So there will be a repulsive force. So to bring closer to the end of the coil, we have to do some mechanical work done. So that mechanical work done will be stored as electrical energy here. That means, you know, mechanical work done is getting converted. Mechanical work done. Mechanical work done is getting converted into electrical energy. Okay, so this is the BT over here. So here, see, this is coming from energy conservation. See, suppose Lenz's law was not based on this energy conservation, then what if we think that there will be south pole when the north pole is brought near the coil? Then what would have been happen? See, then if instead of north pole, if south pole is induced here, then the south pole will actually attract this bar magnet, and hence it will actually gradually move towards the coil. That means, you know, the coil will actually, see, this bar magnet will be accelerated towards the coil. If instead of north pole, south pole is being produced, there will be attraction between the south pole, which is induced in the coil, in front of this loop and the magnetic field. Sorry, north pole of the bar magnet. So you know what will happen. So north pole of the bar magnet will be attracted by this south pole, and hence it will be accelerated, and gradually its velocity will be increasing. So you can see without any effort. See, without any effort, we actually the kinetic energy gain is happening for the bar magnet. So what I am saying is that if the south pole would have been produced here, then additional kinetic energy from nowhere would have been gained by this bar magnet. But that is not possible. Some energy has to be converted into kinetic energy. Similarly, here, if the instead of south pole, if the north pole is being produced here, then while taking away the bar magnet, it will be pushed by the bar magnet, sorry, but the north pole produced here, and that would actually give the bar magnet an additional acceleration, okay, or additional kinetic energy. But that kinetic energy has got no source here, okay. But that is not possible, okay. So kinetic energy should be conservation of sorry, kinetic energy is due to actually the mechanical work done, okay. Okay, so this is actually Lenz's law, and Lenz's law actually supports the conservation of energy. If see, according to Lenz's law, if north pole here and south pole here was not being produced, then additional kinetic energy from nowhere will be actually imparted to this bar magnet, which is not possible. Okay. Now we'll learn about motional EMF. So what is motional EMF? What is motional EMF? Actually, motional EMF, if a conducting loop is if a conductor is part of a closed loop, okay, see this point you have to remember. If a conductor is a part of a closed loop, if a conductor is a part of a closed loop, then if the conductor is moved, if a conductor is moved or a conductor is moving, then the area enclosed by that loop along with the uh, other part of the loop also will change. Due to that, there will be change in the flux, as I discussed. So BA cos theta. So this is actually the formula for flux. If the area changes, then also magnetic field will change, and that is actually easiest way to change the flux. See, the induced EMF across the end of a conductor due to its motion in a magnetic field is called, in a uniform magnetic field is called motional EMF. See, I'll just explain here. Suppose, for example, so PQ is the conductor, and you have this U-shaped train, conducting train. Sorry, not train, conducting rail. U-shaped conducting rail. U-shaped conducting rail. U-shaped conducting rail, you look, this is MSRQN or MSRN. This is the actually rail. Okay, this is the rail, U-shaped rail. This U-shaped rail on which actually the conductor PQ, which is actually moving on this parallel track of this rail, okay, or parallel track. You know, this is, you see, the whole arrangement is actually in a region where there is a uniform magnetic field, but that magnetic field is actually perpendicular to the conductor, length of the conductor, and it is into the plane of the paper. The magnetic field here is uniform and into the plane of the paper. Now see this PQ conductor is actually making a closed loop, PSRQP. So this is a closed loop, okay, loop. PS. This is a conducting loop. Okay, this is whole thing is a loop. All right. Now, since the magnetic field, you can see this loop, you can take in the plane of the paper, and see cross means what? Magnetic field lines are actually going into the plane of the paper. You can think this screen as plane of the paper, so it is actually in the plane of the paper, and the magnetic field lines are actually into the plane of the paper. Magnetic field lines are going into the plane of the paper. That means there is a flux linked with this coil PQRS, okay, PQRS or PSRQ. So in this loop there is a flux link because these magnetic field lines are there here. Flux linked in this loop. Now if this PQ or conducting rod is moved towards this RS or SR with the velocity V, uniform velocity V. If this PQ conductor is moved towards SR with the velocity V, then what will happen? You know, suppose sometime it is here, PQ. Then the area, look, the area is actually changing. So by changing area, what we do? We can change the flux linked in that loop. So in this case, suppose at any instant of time, the length of this rectangular track is some x at any time, okay. So what will be the link flux in that? Flux linked in that? Flux linked will be phi is equal to B into A. A is what? Length into breadth. Length is x and breadth is L. Breadth is L and length is x. Lx. Now, according to Faraday's law, we can get the EMF induced in that. That is actually minus d phi by dt. So ddt of Blx. B and L are constant. Only what is changing is that dx dt. This is becoming dx dt. This minus will cancel each other. So dx dt is actually velocity. So VL. So this is actually velocity. This one, velocity. Okay. So this V is the velocity of this conductor, and this velocity actually decreases or as velocity increases, the length dx is decreasing. Okay, as the time process, the dx is decreasing. That's why the minus sign comes here. So motional EMF is actually given by VVL. Okay, EMF is equal to VVL. So what is the motional EMF we have got? And I'll just recap. If the EMF induced across, so the EMF induced across the ends, across the ends, actually EMF induced across the end. Okay, so this is the thing. EMF induced across the ends of the conductor is BVL. So we have got BVL is the motional EMF, where B is the magnetic field, V is the velocity of the conductor, and L is the length of the conductor. Sorry, breadth of the conductor. Here, sorry, length of the conductor. You can say breadth is 20. Okay, so this length, this is breadth of the conductor PQ. That means L is actually P. L is between PQ. Okay, and X, X is arbitrary, and time to time it changes. Look here, I need to consider here what is the current flowing in the coil there. See, there is induced EMF, induced EMF, but the induced, what is the direction of induced EMF? The induced EMF will be in such a way that, see, my magnetic field are actually going into the plane of the paper. Now the induced EMF should come out of the plane of the paper. Okay, I have to take the direction of the magnetic. Okay, so we have to find out the direction of the EMF. So the direction of the induced EMF has to be the induced EMF will produce magnetic out of. So that is that coming out of the plane of the paper. That actually indicates the current will be flowing from P to S, S to R, and R to Q, Q to. So we have got the EMF. So what will be the current in this case? Current in the current will be EMF by R if R resistance of the conductor. So this is BVL by R. This is the current. The current to the conductor. Now, what will be the magnetic force on this? So what will be the magnetic force on this? So current I is BVL by R. R is this is EMF, this is R of the conductor. So okay, so this is the current. Now what will be the magnetic force due to the induced magnetic field? Okay, what will be the force on the PQ, conductor PQ? So that will be actually I L cross B. I L cross B. So this will actually give you the magnetic force. Sorry, the force acting on the conductor. So L is the length of the here actually small a. And since see length and see magnetic field is into the plane of the paper and this is in the plane, so that's they will actually be perpendicular to each other. So IBL, and this IBL. So what is I here in this? Actually, I is BBL EMF by R into. So what is the current then? Sorry, force then? B square BL, B square BL. This I will not be there. So this is I is BB L by R, and this is B into L. There will be B into L. B into L. Okay, B into L. So this is the actually force. Okay, so IBL, BL is there, BBL. So B square L square V by R. So this is the force, and you know this force will be in which direction? This force will be along this direction itself. Okay, this direction itself. So what will happen? You know, this force will actually move it so fast that it will just go and fall on that. But that we don't want, right? Okay, so we have got. See, just to hold this conductor in its position, actually you have to do certain work done by the external force. So what is that work done? Work done will be actually given by. Okay, so before that, let me just find out what is the charge flow is happening in that. What is the charge flow is happening in that? So we have got the force. Now we'll see what is the okay force we have got. Current we have got. I'll just write in press here. Current is actually BVL by R. Conductor is of resistance R. Then force is actually IBL. So B square L square V by R. This is the current. This is the current and force. The force acting on movable arm. Power delivered by the external force to maintain the movable arm. Power applied by the external applied force. To hold the so what force is the power delivered by the external metal rod in its position by F into V. So what is the force? Force is C square L square V R V square. So B square L square V square divided by R. by the external source, and power dissipated. Okay, power dissipated by the loop. Power dissipated will be I square R, right? I square R. This is I square R. I is what? I you have got like this. So I square means B square, L square by R square into R. So this would give B square, L square by R. So this is actually power dissipated. So power dissipated by the conductor, okay, or through the conductor, power dissipated by or by the conductor. Okay, so this is about power dissipation by the conductor. All right, so I think one more term we can actually find out from here. That is, what is the charge? What is the charge? Induced charge. Magnitude of the induced charge. We can find out. Induced charge. We know, see, EMF is equal to magnitude of the EMF is equal to d phi by dt. Okay, d phi by dt. Again, we know current is actually dq by dt. dq by dt. Current is dq by dt. Oh, sorry. dq by dt, right? So look here, if I write dq, the induced charge is I dt. So what is I then? What is I again? What is I? I is EMF by R into dt. So EMF is what? So 1 by R d phi by dt. This is EMF into dt. This dt goes off. So ultimately what we get? We get dq, that is the induced charge, is equal to 1 by R d phi d phi. Okay, 1 by R d phi or d phi by R. d phi by R. So you have to, if you want to get total charge induced, then you have to do integration out of it for the whole flux linked with the coil. Or so this is actually, see what it means is actually, so this means the induced charge, the induced charge induced charge depends on the net change in the flux, net change in the flux, in the linked flux, we can say, linked flux but it does not depend on the time interval or time. Any kind of time factor is not here. Okay, it does not change in the time. I mean time rate of change of, this is a net change, not the time rate of change of magnetic flux. Okay, see, simply if I say rate of change of flux, this is d phi by dt. This can be achieved by see, this may be some value, but there is a change in this d. So by change in the time, we say rate of change. Okay, so d phi by dt, this is change in the net change in the flux, and this is rate of change. This d phi by dt is called rate of change of flux. So it depends on the net change. That means, you know, in the loop linked flux was earlier, suppose at t1 time it was phi1, and it is increased to phi2 in time t2. So what? So this induced charge dq, it just depends on this difference. Okay, phi2 and phi1, it is directly proportional to phi to phi1, but it does not change. It is not necessary that you have to take the rate of change. It does not depend on the rate of change of the class. Okay, so now we'll just discuss another part. This is kind of a numerical, like another part, or this, like, there will be numerical problem in various competitive exam depending on motional EMF. So one example of that is this induced EMF across the ends of a rotating rod. Suppose there is a rotating rod here. As you look here, there is a rotating. So one end of the rod is pivoted at the center of this circular path. Okay, pivoted. That means this is fixed here, and the other end is actually rotating about the axis passing through the pivoted rod. Suppose this rod is in the horizontal plane, so the axis of its rotation will be in the perpendicular. It is passing through this end of the rod, and it is perpendicular to the plane of horizontal plane, and see, it is rotated with uniform angular velocity omega. And see, this whole rod is actually rotating in a uniform magnetic field, and that magnetic field is actually directing into the plane of the paper, as you see this cross. Now how to find out the induced EMF across the ends of this rod. You know why this induced EMF is actually produced in this conductor? This is because when it is moving, it is actually undergoing a circular motion. Then due to, see this, you know, there is a linear velocity. You can say that. So linear velocity is this direction, and magnetic field is into the plane of the paper. You look this, okay, and if you just make it, see the Lorentz force, due to Lorentz force, the charge will be pushed towards the other end. This is the pivoted end, so the electrons will be actually pushed towards this end, Q. PQ is the rod. So due to Lenz's law, the electrons will be pushed towards Q. So there will be actually separation of charges. Relatively positive charges will be near the O, and relatively negative charges will be our electron, since it is conducting rod. So the electrons will be pushed towards the Q. So there will be a change. See, there will be charge separation, and wherever there is a charge separation, there will be EMF developed. Okay, so that is the reason why EMF will be induced across the ends of this rod when it is rotated in a uniform magnetic field.